Hello, we're here and we're going to work on lesson 2.6 part 2. And we're still working with exponential models and equations and functions, all basically the same thing. But this time it's going to look a little bit different. So it says we've now studied exponential growth a couple of different times in this course, but there's a flip side to exponential growth known as exponential decay. The thing that distinguishes exponential growth is that the growth starts off relatively slowly, then speeds up dramatically as time passes. Let's see how exponential decay compares. Coffee is a popular morning drink because the caffeine it contains acts as a temporary stimulant. Once the caffeine gets into your system, the amount dissipates exponentially, assuming that you don't add more, of course. Answer every question except for 2 and 6 with a full sentence. Okay, so we have some data here from 0 to 7 hours. So 0 is when you started drinking coffee. There is 180 milligrams of caffeine in your system. And then after you stopped drinking coffee, it just kept dwindling. And here is the data on a graph. So up through 7 hours is the data we have in the table, but then the rest is what they're building upon, the same decay rate. So it says, if you're the coffee drinker represented by the table graph, how much caffeine was initially in your system? And that was 180 milligrams. And this is your lesson check. Oh, no, this is not your lesson check question. Sorry, we already had a lesson check question from 2 to 6. Okay, number 2 says, find the relative change in caffeine for each 1 hour period listed in the following table, round to the nearest percent. So we did this. We're going to do this just like we had before. So relative change from 0 to 1 hours is going to be by taking 144 minus 180 divided by the 180. So we're going to go to Desmos, if you can have that out and open. And we're going to take 144 minus 180. And you can see that it's negative, and that's because it's a decrease. So this is a negative 0.20 or a negative 20%. Now let's see what it is from 1 to 2. So that would be 150. So 150. I keep 115.2 minus 144. A negative 0.2. And then 2 to 3 is okay, and that's rounded up to a negative 0.2. And then we have 3.7 minus negative 2.2. And it looks like we're at a negative 0.2 again. And remember, in real life, it doesn't always work exactly perfect. So 59 minus, what was it, 72? Oh, it was 73.7. That's probably why. Oops. Okay, and up here should have been 73.7. Okay, so was it 59 even? Yeah. Okay, and then 47.2 minus 59 parentheses 59. So it looks like it's a negative 0.2 between all of them. And we didn't do the last one. So 37.7 minus 37.2. 47.2. So yep, a negative 0.2 between all of them. So each of these were a negative 20%. Okay. So let's flip the page and build on this. So number 3 says, complete this important statement about exponential change. A quantity either grows or decays exponentially when the blank blank in that quantity is. So either grows or decays when the blank blank in that quantity is. Complete this. Okay, when the relative change in that quantity is the same. Okay, it either grows or decays. But looking at the graph of the caffeine remaining in your system, describe what exponential decay looks like compared to exponential growth. So when your relative change is positive, then you have exponential growth. When you have a negative relative change, you have exponential decay. Okay. So what's the multiplication factor that you'd need to multiply by a previous hour's amount to get the next hour's amount? Hint, if 10% of something goes a wage hour, 90% remains. Okay, so before, earlier in lesson 2.6, we had our 1 plus 0.07, and that was our growth factor. Because our relative change was 7%. So now we have to do the same thing. We have to say 1 plus our growth rate. So now we have 1 plus, but this time it's a negative 0.2. So our growth factor is equal to 0.8. Because we're not getting bigger than 100%, we're getting smaller than 100%. So we're only keeping 80% each time. So use your answer to question 5 to write a function of the form f of x equals expression, where the expression describes the amount of caffeine left in your system after x hours. Your answer in question 6 in the class portion is a good place to look if you need help. Okay, so we're going to have y equals, but it's f of x using x as hours. And we started with 180 milligrams times 0.80 is our growth factor from right here to the x. So number 7 says, use a graphing calculator to verify that the equation you wrote in question 6 gives you the values in the table and the given graph. Describe your results. Okay. So let's go to Desmos here. And we are going to, I'm just going to delete these that we no longer need. And we're going to type in y equals 180 parentheses 0.8 to the x. And we're going to go up to that equation and use the gear right here, and then choose the table option on the gear changes. So convert to a table. And we had 0, 1, 2, 0, 1, 2, 3, 4, 5, 6. Oops. We had 5, 6, and 7. Yep, and all the numbers match. Number 8 says use the function you wrote to find the amount of caffeine left in your system after 115 minutes. So because our number 8 here. So because our X was in hours, we have to switch our minutes to hours. So 115 minutes switched to hours. So 115 minutes divided by 60 minutes in an hour is 2.5 hours. So 2.5 hours. Okay. So our function at 2.5 hours, we can just go up to the table here and put 2.5, and it will give us about 103.03 milligrams still left. 9 says use the graph to estimate the amount of time needed for the amount of caffeine to drop to 40 milligrams. Describe how you found your answer. So there's some, I mean, you can see here in the table, it was between 6 and 7 hours. So we could estimate, it looks like it was around 6.5. So maybe a little bit more than 6.5, so 6.7. So 6.65, so 6.5 I said. So no, 6.66, 6.63. Oh, I'm really close. So about 6.63 hours. I use guess and check. We can also use, we could also put in our, just type in our equation again. So y equals 180 parentheses 0.8 parentheses to the x. And then, scale. Look at our scale in here. We could then also say y equals, we want to get down to 40. So we could say y equals 40, similar to what we did. And we'd have to go up in our graph here. And then when I click on it, it will make the intersection gray button up here. So I can click on that. And it's actually at 6.74 hours. 6.7 hours when using the graph. And number 10 is actually saying use either the table or graph commands in your calculator to try and come up with some more accurate estimates. So we just did that, number 10. So let's go back to our paper here. So 6.63 was using guess and check with the table. And we can see here, number 11 says, make up a situation that can be modeled by each of the following exponential graphs. As always, extra points for creativity. So we know that money in an investment will hopefully grow exponential. Something that starts out of value and decays, radioactive material. So when you go to have different medical procedures, and sometimes they inject radioactive material in you so that they can put you in a machine and read what's going on, that decays exponentially. So those are a couple of ideas. I'm sure you have lots on your own as well. So that is the end of lesson 2.6. And we will catch you back for lessons 2.7 and 2.8 are going to be together, and they're going to be actually 3 parts. So I think 2.7 will be 1 part and 2.8 will be 2 parts as well. So